It blazed blue. On October 29th, 2025, the interstellar Wanderer 3I/Atlas reached its closest point to Sun, and instead of radiating the characteristic crimson glow of ordinary comets, it erupted in an electric blue brilliance, as though it burned hotter than the Sun's own surface. Solar coronagraphs verified the unthinkable. This chromatic transformation violated fundamental physical principles, escalating the mystery far beyond any cometary enigma in recorded history. Could 3I/Atlas be humanity's first tangible evidence of revolutionary physics, or perhaps even technology? Here's how the observational data compels us to question the boundaries of what we consider natural phenomena. By October 21st, the object reached conjunction, slipping almost directly behind the solar disk. 4 ground-based telescopes. The observation window slammed shut. No optical or radio observatory on Earth could follow the object during its most crucial phase, its perihelion passage on October 29th, where it would sweep within just 1.36 astronomical units of the Sun, tucked inside the orbit of Mars. The responsibility for tracking 3I/Atlas during this blind interval fell to a specialized network of space-based solar observatories. 3 platforms formed the backbone of the surveillance campaign. SOHO, stationed at the Earth-Sun L1 Lagrange point, maintained continuous coronagraphic surveillance of the near-Sun environment. Stereo A, leading Earth by more than 20 degrees in its orbit, provided an essential off-angle perspective, allowing scientists to observe around the Sun's edge from a different vantage point. GOES-19, launched in 2024 and equipped with the CCOR-1 coronagraph, contributed high-cadence imaging and multispectral coverage during the brief window, when its geometry permitted an unobstructed line of sight. Each instrument brought distinctive capabilities to the mission. SOHO's LOSCO suite delivered broadband white light imaging and polarization data, essential for mapping the comet's evolving envelope. Stereo A's COR-2 instrument offered a complementary angle, ensuring the object could be tracked even as it disappeared behind the Sun from Earth's perspective. GOES-19 CCOR-1, with its advanced color photometry and rapid exposure cycles, captured subtle variations in the object's brightness and morphology at perihelion. From October 21st through early November, these 3 observatories maintained overlapping coverage, synchronizing their internal clocks and calibrating cross-instrument readings to ensure no detail escaped detection. Data gaps were minimal, just a few hours lost to telemetry resets or brief pointing adjustments. The resulting dataset provided an uninterrupted record of 3I/Atlas's behavior during its most inaccessible phase. It is from this vantage point, locked in space and time, triangulated by 3 solar sentinels, that the story of the perihelion anomaly emerges. No natural comet or asteroid in the inner solar system has ever displayed blue-dominant emission near the Sun. To understand why this matters, we must examine the physics governing how objects absorb and emit light. The color of thermal radiation depends on temperature, as described by Wien's displacement law. The hotter an object becomes, the shorter the wavelength of its peak emission. For most familiar celestial bodies, planets, moons, even active comets, this means their brightest thermal glow resides deep in the infrared spectrum. The Sun's own surface, at approximately 5,800 Kelvin, peaks in visible light close to yellow. For an object to appear blue through its own heat emission, its temperature would need to exceed 6,000 Kelvin, well beyond anything ever observed on a comet or asteroid. 3I/Atlas reached perihelion at 1.36 astronomical units from the Sun, just inside Mars's orbit. At that distance, the solar constant is approximately 770 watts per square meter. That represents the maximum energy available to heat any passive surface, regardless of how dark, how reflective, or how exotic its composition might be. Even if every photon of sunlight were absorbed and immediately re-radiated, the equilibrium temperature for a typical comet nucleus or dust grain would remain far below 500 Kelvin, barely sufficient to boil water, and nowhere near hot enough to shift visible light toward blue wavelengths. Standard astrophysical models predict a redder glow as dust and gas scatter sunlight and radiate absorbed heat primarily in the infrared. The observed blue shift at perihelion, confirmed by independent instruments on SOHO, Stereo A, and GOES-19, stands in stark contradiction to these expectations. The color transition was anything but subtle. Photometric analysis reveals clear dominance of blue wavelengths, with emission peaking near 450 nanometers. According to blackbody theory, matching that color signature would require a temperature comparable to the solar photosphere itself. No known comet, regardless of its orbital characteristics or composition, has ever approached this thermal regime. Even the most volatile Oort cloud comets, which can flare dramatically as they plunge toward the sun, remain hundreds of degrees cooler and display spectra shaped by reflected sunlight and discrete emission bands from gases like cyanogen and diatomic carbon. Attempts to explain the blue emission through conventional mechanisms, shock heating, meteoroid impacts, or rare chemical reactions, fall demonstrably short. Localized hotspots might briefly achieve higher temperatures, but there is no evidence of the kind of sustained, spatially extended heating that would be required to produce a blue-dominant envelope hundreds of thousands of kilometers across. Nor do the data show the strong infrared excess that would inevitably accompany such an event. The absence of these signatures, combined with the sheer scale of the blue emission, eliminates passive thermal processes as the source. This leaves us with a fundamental problem. Under the laws of physics as currently understood, no inert body at 1.36 astronomical units, with only solar radiation as an energy source, should emit such intense blue light. The thermal budget is simply too constrained, and the required temperatures are physically out of reach. Any viable explanation must account for this constraint before considering more exotic possibilities. The blue luminosity at perihelion isn't merely surprising. It's physically extraordinary, demanding a closer examination of what could cause an interstellar object to defy established thermal limits. August imaging of 3I/Atlas captured a familiar sight, a faint, green-tinted envelope stretching tens of thousands of kilometers from the nucleus. This coloration, commonly seen in comets throughout the solar system, originates from diatomic carbon and cyanogen molecules that fluoresce under sunlight, painting a coma green as the object sheds gas and dust. Photometric records from SOHO, Stereo A, and GOES, 19 all agreed on this baseline appearance. But as October progressed, the object's profile began to change in ways no cometary model could anticipate. On October 29th at perihelion, the color profile underwent a sudden and dramatic metamorphosis. Calibrated photometry from all three coronagraphs, cross-checked against each other and against their own historical datasets, showed the green emission rapidly fading, replaced by a deep, broadband blue. The shift was unmistakable. The emission peak migrated to approximately 450 nanometers, a wavelength associated with objects thousands of degrees hotter than any known comet. The data chain was robust, with synchronized timing and independent calibrations eliminating instrument error or solar background contamination as plausible explanations. Simultaneously, a second anomaly became apparent. The luminous sheet surrounding 3I/Atlas ballooned dramatically in size, expanding to nearly 300,000 kilometers across, roughly 1/4 of the sun's diameter. This envelope wasn't diffuse haze, but a sharply defined shell, brighter and more coherent than anything observed from Oort cloud comets, even during their most violent outbursts. The rate of brightening, measured in the days leading up to and immediately following perihelion, far outpaced standard dust-driven models. Instead of following the expected curve, where brightness climbs gradually as the object nears the sun and then fades post-perihelion, 3I/Atlas surged in luminosity, reaching a peak that rivaled much larger, more massive comets. Instrument teams traced the envelope's growth to a discrete event in August, when all three platforms detected a sudden spike in carbon dioxide emission. The CO2 plume, brief but intense, coincided with the earliest signs of the color shift. The gas signature faded within days, but the expanding sheath and blue emission only intensified as perihelion approached. Attempts to model the light curve using known mechanisms, sublimation, fragmentation, even energetic outbursts, could not reproduce the observed brightness or the scale of the envelope. The thermal budget at 1.36 astronomical units simply did not permit this level of activity, especially not in the blue portion of the spectrum. The direct conflict between observation and theoretical models left little room for conventional explanations. The evidence accumulated across three independent instruments pointed toward a process beyond the reach of solar heating and ordinary cometary physics. The green-to-blue transition, the explosive growth of the luminous sheath, and the nonlinear surge in brightness all defied expectations. For astronomers accustomed to predictable choreography of comet behavior, the data from 3i/Atlas brought not just surprise, but a fundamental sense of unease. The catalog of anomalies was only beginning to take shape. A comprehensive accounting of 3i/Atlas's irregularities begins with its trajectory. The object entered the solar system on a path aligned to within 5 degrees of the ecliptic plane, an orientation so flat it defies statistical probability for an interstellar arrival. Most known visitors from beyond the Sun's gravitational domain cut through at steep angles, reflecting the random orbital tilts of their home systems. Yet 3i/Atlas threaded almost exactly along the plane with the planet's orbit, a statistical outlier that immediately captured the attention of orbital dynamicists. The next anomaly emerged in behavior of material ejected from the object. Standard cometary activity, driven by sunlight heating the nucleus, sends gas and dust streaming away from the sun, forming long sun-and-award tails. By contrast, coronagraph images capture repeated episodes of material flowing sunward, directly toward the solar glare. This reversal isn't merely rare. It's fundamentally at odds with the physics of volatile sublimation and solar wind pressure. No known comet in recorded history has exhibited persistent sunward ejection at this scale or distance. Spectroscopic analysis deepened the puzzle. Across multiple observing platforms, the ratio of nickel to iron in the ejected dust was found to be unusually elevated. In typical solar system comets, iron dominates, reflecting primordial solar nebula chemistry. Here, nickel appeared in near parity with iron, a signature more reminiscent of engineered alloys in naturally formed rock or ice. Laboratories processing these measurements have repeatedly cross-checked calibration files and chain-of-custody documentation. Yet the result persists. 3i/Atlas's dust is chemically distinct, with a metallic fingerprint that resists straightforward classification. The object's incoming trajectory brought another intriguing coincidence. When plotted against the celestial sphere, its approach aligns within a narrow window of the constellation Sagittarius, close to the coordinates of the 1977 WOW signal, a famous one-time radio burst that has fueled SETI speculation for decades. While most astronomers caution against overinterpreting this overlap, the spatial coincidence has not gone unnoticed in the anomaly ledger. Compositional analysis from both photometry and mass estimates revealed yet another departure from the norm. Water, the dominant ice in nearly all comets, accounts for only approximately 4% of 3i/Atlas's volatile content by mass. By contrast, typical comets carry water fractions of 80 to 90%. The remainder in this case consists of carbon monoxide, carbon dioxide, and other rare volatiles, an unusual mixture for any known solar system body. Each of these findings, low inclination approach, sunward ejection, high nickel-to-iron ratio, sky alignment with the WOW signal, and water-poor composition, stands as a discrete, independently verified anomaly. None alone is definitive, but collectively they form a ledger of irregularities that strains the boundaries of natural cometary physics. The evidence is cataloged, cross-checked, and ready for the next stage, a rigorous audit of data integrity and the search for systematic errors before any further conclusions can be drawn. Avi Loeb, a Harvard astrophysicist known for his risk-weighted approach to cosmic anomalies, added 3i/Atlas's Perihelion event as a 10th entry in his ongoing catalog of unexplained phenomena. After reviewing the blue emission data and the complete anomaly ledger, Loeb revised his estimate for a technological origin to slightly above 4 out of 10, higher than for any previous interstellar visitor, yet still short of outright endorsement. He notes that if the blue shift is confirmed as intrinsic emission rather than a sensor artifact or solar contamination, it would stand outside the boundaries of current cometary physics. For Loeb and a growing cohort of researchers, the pattern of irregularities, low inclination entry, sunward ejection, engineered alloy signatures, now warrants an open, probabilistic discussion of all possibilities, including artificial power generation or thermal management systems. The debate over interpretation, however, is matched by tension over data access. On October 2nd, 2025, GOES 19 sous vide sensor captured a packet of high-resolution multispectral images as 3I/Atlas neared perihelion. The data, with effective resolution down to 1.2 arcseconds and coverage across 12 spectral bands, was immediately classified. Intelligence agencies cited concerns over sensor calibration and national technical means, while scientific advocates argued that only open, independent analysis could resolve the blue emission's true nature. Representative Eliza McAdams, serving on the House Science, Space, and Technology Committee, has led the push for declassification, framing the issue as a test of public trust in science. Meanwhile, outside formal channels, amateur astronomers and citizen scientists have pooled observations through the Minor Planet Center and informal networks, though without unified coordination or institutional oversight. Their contributions, while decentralized, add to the growing call for transparency and independent replication. As the scientific community weighs the probabilities and the public demands access, the standoff between secrecy and scrutiny has become as much a part of the 3I/Atlas story as the object's own unexplained behavior. Three competing frameworks now define the 3I/Atlas controversy. The first proposes an unknown natural process, perhaps a new class of volatiles or an unexpected photochemical reaction behind its blue glow and unusual activity. The second views 3I/Atlas as a rare statistical outlier, a natural object whose oddities require no revolutionary physics. The third hypothesis, once dismissed but now under careful scrutiny, suggests technological origins, engineered materials, active thermal management, or even deliberate energy output. To resolve these questions, astronomers have established strict, falsifiable criteria for the next observational campaign. On December 19, 2025, as 3I/Atlas approaches Earth, both the James Webb Space Telescope and the Hubble Space Telescope will observe it at close range. Their coordinated effort will gather four critical types of data: high signal-to-noise spectra from ultraviolet to mid-infrared wavelengths, searching for structured emission lines or telltale spectral slopes that would indicate specific energy sources, imaging polarimetry to measure polarization angles and degrees across the coma, key for distinguishing exotic dust particles from engineered surfaces with organized structures, precision astrometry tracking the object's path for any non-gravitational accelerations or control motion that couldn't be explained by outgassing alone, mid-infrared thermal mapping looking for heat signatures unexplained by solar radiation input, which might indicate internal energy sources. Decisive outcomes rest on these benchmarks. Organized radio signals, clear excess infrared emission unaccounted for by solar heating, or abrupt non-random trajectory alterations will support a technological explanation. Natural spectral bands consistent with known molecules, polarization patterns matching plausible dust compositions, or absence of infrared excess would favor a natural origin. For the first time in astronomical history, citizen scientists worldwide are joining professional teams, sharing photometric, astrometric, and radio data in real time through coordinated networks. The coming months will reveal whether 3I/Atlas forces a fundamental rewrite of cometary science or stands as the first interstellar object to raise testable, empirical evidence for artificial origin. On October 29, 2025, three independent solar observatories, SOHO, Stereo A, and GOES 19, recorded 3I/Atlas transforming into an intense blue beacon at perihelion, a chromatic shift never before documented in any natural body at this distance from the Sun. The object's color transition, luminous envelope stretching over 300,000 kilometers, and distinctive nickel-to-iron ratio challenge established cometary models at their foundation. Key anomalies, including a water content of merely 4% and persistent sunward material ejection, remain without satisfactory explanation. As of today, high-resolution images from October 2nd remain under classification, and no structured radio signals or infrared propulsion signatures have been detected. With the next critical observation window scheduled for December 19, 2025, using JWST and Hubble, the central question persists. Does 3I/Atlas represent unknown natural physics, a rare cosmic outlier operating within known laws, or evidence of technology from beyond our solar system? The answer will depend on data yet to be collected. For now, 3I/Atlas stands as the most anomalous interstellar object ever observed, fundamentally reshaping how the scientific community prepares for and analyzes the next visitor from beyond our solar system. The blue glow that defied physics may soon reveal whether we stand at the threshold of new natural understanding, or our first confirmed contact with intelligence among the stars. December 19th, 2025, arrived with the weight of history pressing down on observatories worldwide. As 3I/Atlas emerged from behind the sun, now racing outward at 47 kilometers per second, both the James Webb Space Telescope and Hubble had already locked their instruments on predicted coordinates. The object would pass within 0.82 astronomical units of Earth, closer than any interstellar visitor in recorded history. At 3:14 Universal Time Coordinated, JWST's NIR-SPEC instrument completed its first integration. The spectrum appeared on screens at the Space Telescope Science Institute simultaneously with partner observatories in Chile, Hawaii, and the hastily organized Citizen Science Coordination Center in Manchester, England. Dr. Sarah Chun, leading the spectroscopy team, went silent for a full 30 seconds before keying her microphone. We have structured emission, multiple discrete lines, not matching any known molecular database. The lines weren't the familiar signatures of water, carbon monoxide, or any of the hundreds of cataloged cometary volatiles. Instead, the spectrum showed a ladder of sharp peaks in the near-infrared, evenly spaced at 47.3 nanometers, a precision that screamed deliberate rather than random molecular chaos. Within the hour, Hubble's ultraviolet spectrograph added its own puzzle piece, a series of absorption features that formed a mathematical progression, each wavelength related to the previous by a factor of 1.618, the golden ratio. Natural processes don't do arithmetic, muttered James Corey, coordinator for the Amateur Astronomer Network. His team of 47 citizen scientists across 6 continents had been tracking the object's brightness variations with backyard telescopes. Their crowdsourced light curve, when combined with professional data, revealed something no single observatory could have detected. The brightness pulse in a complex pattern, repeating every 3 hours and 41 minutes, with subpulses embedded at exactly 1/10 that frequency. By 8 o'clock Universal Time Coordinated, the mid-infrared mapping from JWST's MIRI instrument had processed. The thermal profile made no physical sense. The object's sunward hemisphere, which should have been hottest, registered at a modest 380 Kelvin, consistent with passive solar heating at its current distance. But the shadowed rear hemisphere glowed at 520 Kelvin, nearly 140 degrees hotter than the illuminated side. The temperature distribution was inverted, impossible for any body heated solely by sunlight. It's generating its own heat, Chin said into the hushed control room, and directing it preferentially away from the sun. The infrared excess wasn't subtle. MIRI detected approximately 18 megawatts of thermal emission that couldn't be accounted for by absorbed solar radiation, even assuming perfect blackbody efficiency. For comparison, that's enough power to run a small city, emanating from an object estimated at less than 400 meters across. At 14:22 Universal Time Coordinated, the Goldstone Deep Space Network antenna picked up an unexpected Doppler shift. 3I/Atlas was accelerating, not from outgassing like a comet, but with a smooth, continuous thrust that showed no correlation with solar heating patterns or rotational phase. The trajectory change was small but unmistakable, 0.04 millimeters per second squared, sustained over 47 minutes. Then it stopped as abruptly as it began, leaving the object on a slightly altered course, one that would, if maintained, carry it to within 0.15 astronomical units of Earth in early January. Polarimetry results arrived simultaneously from 3 observatories. The dust envelope surrounding 3I/Atlas showed polarization patterns unlike anything in the cometary catalog. Instead of the random orientations expected from irregular ice and rock particles, the reflected light showed organized structure, microscopic grains aligned within a few degrees of each other across the entire 200,000-kilometer envelope. That's not dust scattering, said polarimetry specialist Dr. Helena Voss from Chile. That's more like optical engineering, like someone built a swarm of tiny mirrors and oriented them deliberately. At 1947 Universal Time Coordinated, The Allen Telescope Array in California detected something that stopped the scientific debate cold: a narrowband radio transmission centered at 1420 megahertz, the hydrogen line, the universal frequency astronomers have long considered ideal for interstellar communication. The signal lasted 8 seconds, consisted of 1,679 binary pulses, and then ceased. Avi Loeb, monitoring from Harvard, immediately recognized the structure. That's a Sagan prime. 1,679 factors into 23 and 73, both prime numbers. It's meant to be arranged as a rectangular image. Within minutes, teams worldwide began arranging the binary string into a 23 by 73 pixel grid. The resulting image was crude but unmistakable, a mathematical diagram showing the solar system's orbital geometry, with an arrow pointing from the outer regions toward Earth orbit and a symbol, 3 concentric circles, positioned at Earth's location. A second burst arrived 12 minutes later. This time, 2,419 pulses. Another Sagan prime factoring to 23 and 97. The longer image showed the same solar system diagram, but now the 3-circle symbol had moved to a position between Earth and Mars, with a time marker suggesting a date, January 8th, 2026. The third transmission never came. The Allen Array waited, joined by every radio telescope on Earth that could be rapidly reoriented. But 3I/Atlas had gone silent. By December 21st, classified goes 19 imagery from October 2nd had leaked through multiple channels, first to scientific journals, then to mainstream media. The images showed 3I/Atlas's nucleus resolved for the first time. Not the irregular potato shape of every known comet, but geometric structure with apparent bilateral symmetry and surface features suggesting artificial construction. The United Nations called an emergency session of the Committee on the Peaceful Uses of Outer Space. Representative McAdams, vindicated in her demands for transparency, now face a harder question. What should humanity do next? 3 factions emerged immediately. The first, led by SETI veterans, advocated for active transmission, sending a return signal acknowledging receipt and understanding. The second group, citing the precautionary principle, argued for silent observation. The third, championed by space agencies, proposed an interceptor mission, a rapid deployment spacecraft to reach 3I/Atlas before it could pass Earth and potentially accelerate beyond reach. Doctrine appeared before the committee via video link. We have 17 days before January 8th. The object has demonstrated controlled motion, organized structure, mathematical communication, and impossible thermodynamics. If we don't respond, we may not get another chance. If we do respond incorrectly, we might be initiating first contact under the worst possible circumstances, with no preparation, no consensus, and no idea who or what we're talking to. The vote was scheduled for December 24th. Before it could take place, 3I/Atlas provided one final piece of evidence. At 2:33 Universal Time Coordinated on December 23rd, every major observatory on Earth simultaneously detected a spectacular event. 3I/Atlas, now 0.76 astronomical units from Earth, suddenly brightened by a factor of 10,000, briefly outshining Jupiter and Earth's sky despite the object's tiny size. The flash lasted exactly 3.141 seconds, pi, to 3 decimal places. Then the object returned to its previous luminosity. JWST, tracking continuously, captured the flash's spectrum. It wasn't thermal radiation or reflected sunlight. The emission was coherent, monochromatic laser light at 589 nanometers. The sodium D line, one of the most recognizable spectral features in all of astronomy, and it was aimed directly at Earth with a beam divergence of less than 1 arc minute. That's a lighthouse, Loeb said in an emergency press conference, or a signal flare. Someone is making absolutely certain we know they're there and that their presence is deliberate. The demonstration changed the political calculus overnight. On December 24th, the UN vote was unanimous. Humanity would respond. The return message, crafted by a committee of linguists, mathematicians, and diplomats, was transmitted from Arecibo's replacement array in Puerto Rico on December 26 at 1800 hours Universal Time Coordinated. It echoed the structure of 3I/Atlas's original transmission, a Sagan prime image showing Earth's acknowledgement, followed by a second image depicting a question mark, the universal symbol of inquiry. For 3 days, nothing came back. Amateur radio operators and professional observatories maintained continuous watch. The world held its breath. Then, on December 29th, at precisely the moment when 3I/Atlas passed 0.72 astronomical units from Earth, matching the orbital radius, where Earth would be on January 8th, the object transmitted one final signal. This time, it wasn't binary pulses or mathematical diagrams. It was video. The transmission lasted 43 seconds and showed what appeared to be a historical record. A planet orbiting a dim red star, cities of light visible on the night side, then a sudden catastrophic event. Perhaps a nearby supernova or stellar collision. The cities went dark. A final image showed spacecraft departing the dying world, hundreds of them, dispersing in all directions into the galaxy. The last frame showed coordinates. Right ascension 19 hours 25 minutes, declination minus 26 degrees 52 minutes, pointing to a region of Sagittarius, less than 2 degrees from the 1977 WOW. Signal source. 3I/Atlas is now outbound, accelerating at a steady 0.08 millimeters per second squared, enough to escape the solar system decades sooner than gravitational dynamics alone would permit. Its course has been refined. January 8th will bring it to within 22 million kilometers of Earth, close enough for detailed imaging but far enough to avoid gravitational disruption. Observatories worldwide are preparing for that encounter. Space agencies have accelerated mission concepts that were theoretical just months ago. And in living rooms, classrooms, and laboratories across the planet, people are processing the same revolutionary truth. We are not alone, and we never have been. The blue glow that defied physics at Perihelion was never meant to be subtle. It was a beacon, a declaration visible across millions of kilometers. We are here. We survived. And now we found you. On January 8th, as 3I/Atlas makes its closest approach, humanity will watch as a visitor from another star system, carrying stories of civilization that endured catastrophe and sent its seeds across the galaxy, completes its grand tour of our solar system, and continues outward toward destinations unknown. The anomaly is solved. The question now is not whether we are alone, but what we do with the knowledge that we never were. And somewhere in the archives, preserved in amber of electromagnetic waves and gravitational echoes, the WOW signal from 1977 has found its answer. They were already on their way. The International Space Station had been hastily retrofitted with additional communication arrays over the past 2 weeks. Commander Maria Santos floated before the observation cupola, watching 3I/Atlas approach as a brilliant blue star against the blackness. In 16 hours, it would reach its closest point to Earth. Below her, every major city had gone dark in coordinated observation protocol, reducing light pollution to give 8 billion people an unobstructed view of humanity's first confirmed visitor from another civilization. ISS, this is Houston. We're receiving telemetry from Atlas. It's changing course again. Santos grabbed the comm panel. Repeat that, Houston. Atlas just executed a braking maneuver. It's not going to pass us at 22 million kilometers anymore. New trajectory puts closest approach at. A long pause. 380,000 kilometers. That's closer than the moon. The cupola suddenly blazed with light. Santos shielded her eyes as 3I/Atlas erupted in a luminous display that cast hard shadows through the ISS modules. But this wasn't the blue glow from Perihelion. The object was pulsing through a spectrum, red, orange, yellow, green, blue, violet, cycling through visible wavelengths in a deliberate sequence that every human eye could recognize. "They're saying hello," whispered Santos. The Allen telescope array detected the transmission burst 18 minutes before 3I/Atlas reached its closest approach. This time, the signal wasn't Sagan prime or a mathematical diagram. It was sound. Dr. James Corey, still coordinating the Citizen Science Network from Manchester, was the first to decode it. The binary stream converted directly into an audio waveform. Simple, elegant, unmistakable. Music. Not human music, but recognizably structured. Harmonic progressions, rhythmic patterns, melodic phrases that resolved and repeated. The composition lasted 4 minutes and 11 seconds, and within its mathematical structure, embedded at precise intervals, were data packets. SETI teams worldwide began unpacking the embedded information. It contained a star catalog showing 847 exoplanetary systems, with 14 marked by the three-circle symbol, chemical formulas for their atmosphere and propulsion technology, physics that human science could verify but hadn't yet discovered, a timeline showing their departure from the dying world near Sagittarius, 42,000 Earth years ago, and a simple statement translated through mathematical constants into 12 human languages simultaneously. We are the survivors. We are the searchers. We have found 847 worlds with your mathematics. 14 have sent us greetings. You are the 15th. Every telescope on Earth, in orbit, and throughout the solar system focused on a single point in space as 3i/Atlas reached 380,000 kilometers from Earth, exactly the same distance as the Moon's orbit. The object had grown a magnificent tail, but not the dust and gas tail of a comet. This was structured geometric. Thousands of smaller objects trailing behind the main body, arranged in a perfect spiral pattern that rotated slowly like a cosmic pinwheel. Dr. Sarah Chun, watching from the Space Telescope Science Institute, felt tears streaming down her face as JWST's images resolved the trailing objects. They were probes, hundreds of them, each no larger than a refrigerator, separating from the main craft and beginning their own independent trajectories. The tracking data came in fast. 47 probes heading toward Mars, 83 toward the asteroid belt, 12 toward Jupiter's moons, 6 toward Saturn, 21 toward the Kuiper belt, and 1 probe, larger than the rest, adjusting its orbit to enter a stable Lagrange point between Earth and the Moon. The main body of 3i/Atlas continued outward, accelerating steadily, but had left humanity a gift. A fleet of messenger probes, each carrying technology and information from another civilization. The single probe destined for Earth-Moon L5 transmitted its own signal as it settled into stable orbit. This message was the most detailed yet, a complete technical schematic of the probe itself, instructions for safe approach and retrieval, and an invitation encoded in every human language. This vessel contains our library, our history, our mathematics and art and music and stories of survival. We give it freely, as we have given similar gifts to 14 other worlds. Study it, learn from it, and when you are ready, when you have built your own vessels capable of crossing the interstellar dark, come find us. We have left markers at each of the 847 systems we have seeded. We are still searching. We are still surviving. And now, you know you do not search alone. The probe included coordinates, not back to the dead world near Sagittarius, but forward to a rendezvous point 200 light-years away, orbiting a G-type star similar to the Sun. We will wait there for 10,000 of your years. Bring your own stories. Bring your own music. Bring your proof that intelligence, once kindled, can endure across the millennia and the light-years. We have seen worlds die. We have seen civilizations fail. But we have also seen 15 species reach for the stars. You are young, but you are reaching. That is enough. The UN Security Council met in emergency session. Space agencies unveiled plans for a crewed mission to retrieve the Lagrange probe. Universities worldwide began organizing research consortiums to study the data. But the most profound response came from unexpected places. In Manila, a street musician composed a reply song, broadcasting it toward the departing 3i/Atlas through a jury-rigged radio telescope. In Sao Paulo, a mathematics student published the first human proof of one of the theorems embedded in the alien data. In Nairobi, engineers began sketching designs for Earth's first interstellar-capable vessel. Avi Loeb, speaking to a global audience of 3 billion simultaneous viewers, summarized a moment. For 40,000 years, while humans were painting on cave walls and learning to farm, 3i/Atlas and vessels, like it were crossing the galaxy, carrying the legacy of a doomed world. They didn't come to conquer. They didn't come to colonize. They came to remember and to remind others that they were remembered. Today, we learn that intelligence in the universe doesn't just exist. It persists. It endures. It reaches across the cosmic dark and says, "We were here. We survived. And so can you."